This is the video tutorial for chapter 14 of the textbook. It's a mass spring damper system. It's a very simple problem, the kind of thing that you see in your dynamics class for vibrations. So we're going to go down to basics. Okay. I'll do two problems. The first one is a single degree of freedom system where the mass spring and damper system are specified, as you see here with these values. And uh, an initial velocity of 1 meter per second is given to this mass. What we like to do is to plot the force, or not the force, displacement versus time history. The second problem that I do is a 2 degree of freedom system, same setup, except that there is a load that is applied at m1 instead of a initial velocity. Is to find the displacement of the mass as a function, the masses as a function of time. Okay, so let's do the single degree of freedom system first. And what I'm going to do is I'm going to create 2 points here. One of them is 30 millimeters along y. That's going to be point A. And another one, which is 60 millimeters along y. That's going to be point B. I just have to remind you that in mechanics, springs don't have any length, at least in the context that we are interested in. However, for the sake of illustration, so that we can see them, I am going to give them length. For example, point A and point B, the ends of the spring, we're going to assume that they're, apart like that. Okay. So this is really all we need for the models. What we do is we go to structure model creation, and it's a standard radio, default radio buttons here. There is a tab here called abstraction. This is where you apply point inertias or masses. You click on it, move this apart. This is the point A where the mass is going to be located, and the value of the mass, according to the table that I showed you in that chapter, is 10,000 kilogram. Okay, nothing down here, so you can see that there is some icon which looks like a mass. Okay, now when it comes to the spring, you click on the connections and you scroll down here, open this up. There's a spring there. Okay, spring. One end of the spring is the point A, and if you don't pick the second point, then it's going to assume it's the ground. See that? It's right there. It says ground. But if you want to specify it, and I do, so you go to the next one, and this is going to be my point B, which is effectively, think about it as the ground, what I'm going to fix. Okay. Now it is an axial spring. Okay, and the value of the stiffness, I believe it was 1 e to the 7. E to the 7. Okay, see. Yep. And then really this mesh is irrelevant, but here I'll say update. There's nothing to update, so we say okay. Good. So there's a situation. Okay, and we are done here. So we're going to go to scenario creation, structural, setup. We're going to select our so-called mesh. There's really no mesh here, but you have to do it. Okay, notice that this turns green. And then for procedure, let's first find the natural frequency of this. This is a single degree of freedom. So we're going to say frequency step. It's foolish to say find 10 frequencies because there's only a single degree of freedom. It's a single frequency. So I change this thing to 1. And then I start applying my restraints. So let's see now, restraints. This end does not move in any direction. The ground does not go anywhere. So you click on it and you select that and you say don't go anywhere. Although rotations, this is axial spring rotations, shouldn't have any effect, but I'll fix them too. Okay. Now this is the end that moves along the y direction. So you click on it, you select that point, and you say, don't move in X, don't move in Z, and rotations, I'm going to fix it. Okay, good. So there is really nothing else to do. If I run this thing, it's going to be uh, basically a single frequency that's going to get extracted. So you go to simulate. Let's check all of these things. And I think based on the formula square root of k over m, you're going to get 5.3 hertz, 5.03 hertz, something like that. Okay, and now we're going to run it. Okay, that did finish. We close that, and now we're going to run it. Nothing fancy is going to see, you're not going to see anything fancy on the screen, just a single number, 5.03. Okay, almost. Okay, 5.03 hertz. Good. So as far as this is concerned, we're done with that part, extracting the frequencies. The next thing we want to do is to apply an initial velocity to that point A of 1 meter per second, right? So let's do that. So we close this. We're going to go to scenario, okay? And under uh, uh, procedures, we want modal dynamics, okay? I'm going to make this thing 2 seconds, and I'm going to make this thing a little smaller, 0.01. Say okay. Of course, there's only one mode to extract, so that's fine. And then we want initial condition, and initial condition is velocity. So at this point, because the other one is the one that's fixed, we're going to give it 1 meter in the direction y, right? It can only move in direction y, 1 meter per second. You say okay. And since we're going to be plotting some stuff, okay, so might as well ask for some extra data. So I'm going to click on procedure, and I'm going to click on, simulate, and click on this additional data, additional output. So it is a history plot that we want to get, history plot, and it is the plot, history plot at every increment of this point. And this is going to be translation, of course. If I say force, the force there is, well, applied force is really 0. Okay, so that's fine. So we're going to say all right. And that's pretty much it. So let's run it. Obviously, I have to do that. Should be doing check of these two, but let's run it. Those two initial checks are very important, and if I'm not doing it, it's not a good idea. Okay. There's no damping here, so this will vibrate forever. Okay. And after I do this, I'm going to go and apply some damping there and see what the effect is. All right. So close this. To get the plot, so you go to plots icon right there, history, XY plot of history, and I requested output right there, and make sure you change this thing to displacement translation. There's no rotation here. If you do the magnitude, it'll just positive or negative are going to be treated the same. But let me change this thing to component direction 2 that you're more used to. Something like that. The magnitude is the same thing in this one. Well, the magnitude is going to be just the humps on the top. Okay, so as a matter of fact, you can see that if you go this thing to magnitude, you might say, oh, why does it look like that? So because all the positive and negatives are lumped together. But anyway, the component 2 is what you're used to in your vibrations class. Okay, good. Now, what we like to do is to go add some damping. So I have to go to scenario. On this scenario, I go to procedures, and way at the end, there is a damping. Damping. Now, frequency 5 hertz, the critical damping ratio is 4.7%. So I'm going to put 4.7 here. That's C over C critical. We say OK, and you're going to run it. Simulate and run it. Don't skip these steps. People become complacent and things go crazy and they don't know what happened because they didn't check these things. So obviously here, because of the damping, that displacement is going to die down. Eventually it's going to stop, of course. Once we're happy with this problem, we're going to create our 2 degree of freedom system. It's very similar. Okay, close this, history plot, and displacement in direction 2, apply, and there you are. Okay, good. So the next step, the next process, I'm going to start this thing from the very beginning instead of adding the third point to this part. So let me start from scratch. I'm now going to be doing the 2 degree of freedom system, so I'll create 3 points A, B, and C along that y direction. So let's start with the first point, 30 millimeters away. That's going to be the point A. The next point is going to be 60 millimeter. That's going to be where the second mass sits. It used to be the wall before in the single degree of freedom system, but now it's the second mass. And the third one is going to be 90. There we are. Okay. So we're going to place our masses. The model is done here, so we're going to switch to structure model creation. Standard radio buttons here, nothing fancy. And under the abstractions, this is going to be my first mass, and I believe that was 2 times 10 to the 5 kilogram, or 200,000, 2 times 10 to the 5, okay? So that's going to be 2 e to the 5, okay? And then, okay? And then the second mass is here. What was that? That was 2.5 10 to the 5. Yeah, so this is going to be 2.5 e to the 5. Make sure okay. Yep, say okay. And then we're going to do the springs. Now remember, the springs were under connections. You scroll down over here. There's a sub menu here, and the spring was happened to be on the front because I used it just a few minutes ago. So you click on it. This is going to be the first spring going from point 1 to point 2. Okay, wait a minute. So let me move this thing a little bit like that. Point 2 is this point, okay, and it's axial, and the value of it is that's K1. It's 150 10 to the 6, 150 10 to the 6. You got to be a little bit careful here because 150 10 to the 6 is actually uh, Newton, right? So you have to divide that. You have to divide that by 9.8, okay? So be careful here because this stiffness is Newton per meter. The other one on the other side is a different unit. So to be strictly correct, I should say either I have to fix this and say kilogram per meter per second squared, or divide this by 9.8 and put it in there. I rather do this. I rather do, uh, yeah, so I'm going to do it here. Dividing this thing by 9.8, I'm going to divide it by 10. How about that? Okay, so roughly 10. Okay, so I go here, and so that's going to be, I forgot. It's going divided by 10, 15, 10 to the 6. Okay, 15, 10 to the 6. So 15 e to the 6. This is a kind of weird stiffness unit that it has. I should have gone and changed it, changed my unit. You know what? As a matter of fact, uh, and this also applies to the previous problem that I did. Obviously, this is wrong, so I'm going to cancel that. I'm going to cancel that, cancel that, cancel. Let me go to my units because I made that mistake in the first single degree of freedom system too. So let's see under stiffness if we can find stiffness, either stiffness or axial stiffness. I don't see any axial, but see stiffness. Let's check that. Stiffness constant, Newton. That's what it should be, right? That's what it should be. So let me see what it is now. Newton per meter. Yeah, that's what I want. So amplitude, apply, okay. So this stiffness, that's still coming out to be what I had before. So you may want to check this. Let me see now. Linear general. No, linear axial. I don't like this. Let me type. See if I can type something else. How about that? Let me type this. Okay. Here we're going to do 150 e to the 5, right? Oops. Try it again. Let's try it. 150 e to the 5, e to the 5, right? Newton per meter. Let's see if it converts it to something. Yeah, it did. I guess it's the same thing. That's fine. Didn't convert. It's the same thing. That's okay. So that was not a mistake. That is fine. This is the correct thing. So let's see now. Support 1 is right there For the second point, sub point B is right here. I'm sorry, ignore my comment about this being wrong. This is the same thing, because when I put down 1.5 or 150 e to the 5 Newton per meter, it automatically converted to this. So it must be right. All right, so let's do the other one. The other spring is from here to here. So from that point to this point, okay. And the stiffness for that spring is 75. I think this was a mistake. It was 150 e to the 6. I did not see that. So we'll fix it. 75 e to the 6. I have to fix the other one too. So this is going to be 75 e to the 6. 75 e to the 6. That's okay. That's okay. Update mesh. I have to fix the other one. The other one was a mistake. So right there, the first one, the first spring. That should have been one more 0. So it should have been, okay, it was 150 e to the 6, right? 150 e to the 6. Yeah. Okay, good. Okay, good. So this takes care of the model. Now we're going to go to our scenario, structural scenario, structural. Okay, first we're going to extract the frequencies, natural frequencies. So set up, we'll have to choose our model, of course. Finite element model, there's only one here. So that's this. Okay, this thing turns green. Now we go procedures, and let's find the frequencies, and let's find the two frequencies. And we're going to restrain it so that there are actually two frequencies here. So we go to restraints, this endpoint, let me actually use the fixed displacement. So this endpoint, everything is fixed. Okay, by the way, I made a comment some time ago about hiding the points. It looks like the current version of 3DEXPERIENCE will even take the point and treat it correctly. I just warn you that that is not the case in some other software, such as CATIA. That is not the case. Okay. Then this point, no rotation about XYZ, is free to move along Y, and the same thing with that point, that other point right there. No rotation about XYZ, but it is free to move along Y. Okay, so if we run the analysis here, we're going to get two frequencies, and these two frequencies, if you compare with the analytical solution, they match it very, very well. So let me go ahead here and say check the model, something that I ignored doing in the previous single degree of freedom model. In case there are any messages, error messages, they're going to pop up here, and you can fix it. Okay, I'm sure this is going to go through too. The two frequencies that I get should be 1.9, almost 2 hertz and 6 hertz, something like that. Okay, so close this and then run it. Yeah, 1.94, 6.1, that's good, so it worked fine. We then apply that load, that step load, See that's step load. We're going to apply it to mass 1 uh, and run it, and then we come back and do a damping later on. Okay, initially we have zero damping, so that's fine. So we're going to go to scenario. Sure, you have the procedures tab. When you select the procedures tab, then there is a setup next to it. You click on it, and over here there is tabular amplitude. So you click on it, select it, and you put your table. The table that I'm going to do is roughly what I have, what I had before. So it's pretty much the same, except that there is a small drop. It's not a sharp drop. So it's going to go, for example, let me see now. I will do it like this: 0, 0, amplitude of 1, and then at something that's very close to your point 1, which is your drop point. See that? See, point 1, there's a drop, but I'm going to go a little bit to the left of it and drop it, drop the amplitude. So it's going to be 0 0.099, oops, right here, sorry, 0 0.099, and drop to 0, and then past that 0 0.1, 0 0.1, keep it at 0, and then all the way to the end, which means after 2 seconds, also keep it at 0. Okay, so this is almost that graph that I showed you, but I made a slight change here. You can try the other one, see, but there must be a reason that I'm doing it like this, and pretty much this is okay. And now we're going to apply our load. The load is applied to this point. Let me undo this. Where is this? Loads. Sorry. Uh, Notice that because we are in the frequency, see, we just extract the frequencies, right? So there you cannot apply load. That's why you have to go to procedure and create a modal dynamic step, and time step 0, 0.1, the same one that we did before, and time increment of 0.05. Same thing that we did before. Let me just double check, make sure it's the same numbers that I used. Actually, I'm going to change this, because in the previous case we used 1 second, time step of 1 second, and time increment of 0.01. I'm using exactly the same numbers as in the single degree of freedom system. Now we can apply load. It will not let me do that before, because I was in natural frequency calculation when loads don't participate. So here's a load. Procedure, where is that load? Loads. There is a force at that point in the direction y, 2000, I think it was 400, was it not? 2400. Let's see now. Yeah, 2004, 24,000. Yeah, 24, 24, 25,000, 25,000, 25,000 Newton in the direction y. And the thing is that I want to use the amplitude that I created. See that? Not the default, the amplitude that I created, and that was amplitude 1. Okay, so we say okay. All right. Now, before we simulate, let's ask for some data. So let's go ahead and ask for some data. It's a history plot that we want. We want this point, this point. We want the displacement. Yep. Okay. And I want the reaction force at this point. Okay, another one. Again, history at this point, which is the wall. And I want the reaction. The displacement is going to be 0 there, so it really doesn't matter. So basically, I asked for output 2 and output 3 as an additional data. Okay. So there's no damping here. So let's see how it goes. Where is this thing? Let's check our model. No problem there. Check our simulation. I'm sure it's going to run. And then simulate and plot. It's always a good idea to check these warnings. And run it. These are the two frequencies that we initially got, so that's fine. And right, so we're going to go to history plot. Output 2 was the displacement of the point A. So let's get the component 2. I'll apply low damping here, and therefore we're going to get displacement like that. Okay. And okay, so if you want, for example, what I wanted to do was actually get the displacement at the point A and the point E, okay, and the point B. So let me cancel this, close this, go back to simulation, something that I forgot to do, go back to scenario for additional data, history plot. I want this point. And can I do the other one? Well, that point I already have, so cancel that. Let's try point, the other point, So history. So this point, this middle point, remember I had a point here, that point, and displacement of that. Yeah, displacement of this. So I'm asking for displacement at the point A and the point B. First time that I run it a couple of minutes ago, I just asked for A. I want it to be. It gave me the A, but I want both of them. Okay, so let's run it. I wanted them both to be on the same plot. Let's see. Let's see how it works. When it comes to damping, I'll show you how to do it, and then you can go and add your modal dampings yourself and plot the graphs. Okay, check it against the book. It's coming along. I did not bother doing the first two checks, so this is okay. Close that, and then history plot. Now let's see. I want translations, not magnitude, component 2, apply. Both of them are at the same time. Now, when it comes to damping, let's also do the one for wall reaction force. So reaction force at the wall. So it's right here. This was the reaction force at the wall. Okay. Now, if you want to add damping, what you do is you go to scenario. sorry, I'm not going to do that, but I'll show you how it works. So procedures, there's a damping. You add the first two frequencies, and it was 1 point something, and then the two that I got, and add the damping as I suggest in the book. Okay, so good luck.